rotation. You like lateral triangles because they have the symmetry of this rotation and so on. And so then there is a few types of actions or transformations. We can transform the object to be symmetric. So we have first not symmetric object, and then we want to make it symmetric somewhere. So before yesterday, we considered objects, and we tried to find something which is the sense of its asymmetry. And this simple symmetry set and but today you find a place where you find a kind of objects which says where we can or what we can do with the object with say shape to be symmetric. And then there are several ways of symmetrization. And you can know, I tell you those which are in literature, but those which I tell today, there is no new publication. So that's, yesterday also there was most of the new. And then, you see, this is the one of these symmetrizations, looks like that you take parallel tangent transfer. It's called parallel tangent transfer. So you can take the point and then parallel lines and then move these black things to such a way that that point is in between. If you do this with all the parallel lines, then you get this red object, and this red object, I'm sorry, yeah, this is red object. This is opposite. The red object, you see, is asymmetric. You see, red object is asymmetric, and then you choose the point and you take this dotted line and move such a way parallelly that this point is inside, is the center of this interval. This is very important. And if you do this for all dotted lines around the red curve is a non-symmetric curve. You see, non-symmetric one. Then you get symmetric one. Blue one is symmetric. The central is symmetric. It's not a cycle because it's for cycle, but this central is symmetric. This is one of the kinds of symmetrization, which is known already. Studied in convex sets investigation, but this is some sense not so interesting for today. And also there is another symmetrization, like you take the line. So again, red is not symmetric. You take the line through that, and then you see you have again this parallel. You have the depth interval should be orthogonal to the. Then you take this orthogonal interval and you move it such a way that that point of the intersection of it is inside the center of this interval. Then you get again something which is symmetric according to reflection according to this line. Line. This is better to see that this is orthogonal. If I'm here, that I think this is so there are, you see, and now now I show you the completely new transformation. Center symmetric transform, CST. So point inside the convex curve. We choose a point inside the convex curve. Again, is the red. We choose the point. And it's not like before. We just take this interval in each direction. Forget about parallel tangents. No parallel tangents. Just take this interval, as we get the point, and move it. You see, you take like this and move it like to that, such a way that this point is in the center of this interval. This interval is this interval, but I move it here such way that this point is inside. I fix this point. You understand? But maybe those who are watching me from that far away, they cannot ask any questions. So maybe you ask questions. So if you do, then it would be easier. If someone asks questions, that's of course trivial, but in some sense. But if people follow it, that's not so trivial. Exactly. This interval in that direction, or in direction of this interval, like that. You see, I take this, move like this. And I take another one, this one. Yeah, I take this one and do the same. With all the lines. So I take this, you see, I take this interval and move, you see, like that. You understand? And then I get a blue one, which is tensor symmetric. This is completely new transformation. And this is very difficult transformation in some sense. But it is very special. I show you why. Because it depends on the point inside the oval. The point. If the point is somewhere, then this curve is not convex. No, the convex is beautiful usually. You know, this is something very beautiful from architecture. So now, if you have this, you see, the point is closer to the kind of boundary of the body of this oval, like here. Then, if you consider this interval, and then you consider this interval, then it appears that this image of the transformation is not convex. So from some point where you are close to the boundary of this oval, you have problem. This is just vision problem. I mean, if you are close to somewhere, then you don't know where you are because of this non-convexity. So then, if you have the convex world, now you jump to another world, non-convex. So the problem is, what is the soul of convexity, the center of convexity, the most important part of this oval is somewhere here. Here we choose the point which is that is corresponding to this oval is convex. But here we closer, like here, closer to the boundary, no, it's not convex. So we lost here. But there is some set here where which we pass through, we are in different world, non-convex. And we are interested where this set is. What is this? If there exists the area of this area, we call the soul of convexity of the convex body or such. That's my favorite name, but this is very important. So let's see. So let's check some such convexity soul of the convex body. So let's take cycle. It's very nice set, very symmetric. And then you see, if you have the point, if you are at a point somewhere here, and you do this construction, so you take this interval and you move, so then you got this one. But if you take this interval, this constant. Because if you take this interval, this interval is inside, this point is inside. But you see that this construction gives you something which is different than side, of course. The blue one, which is but still convex. still convex. There is only some cycle here, the boundary of the set, where this blue set stops to be convex. It is that set. And if you pass through this set, you get a little convex. This is the, of course, non-convexity, but still is centrally symmetric. But non-convex. But non-convexity takes you outside of this beautiful world, different world. So you are interested, in fact, in this area. This area. So if you look on the cycle in your life, there is not one cycle. Cycle is with infinite family of cycles. All the cycles, I constructed the cycle. Having the cycle, you thought the cycle is only this line with the point, with the center. No. The cycle is on this cycle, look at that. Also, the set, the central symmetric transformation on this side. So you get this side, this side, and this side. So infinite family of cycles. And also we can go out. So we can ask which that this is this boundary of the soul of the bigger cycle. So we can draw this, draw this, draw this. So this is so infinite family. Of course, to compact the space, then this one, the smallest one, and the biggest one, they collapse. They meet together, and the space is just compact. But that is for cycle, you see. And then simple proposition says that if G be an ellipse, because this is for always true for say for centrally symmetrical. If you consider the ellipse, the cycle is the ellipse. So then if you have an ellipse and R, the region inside G, gamma, consisting such P that the central symmetric transformation of gamma with respect to P is strictly convex, so that's a set. This is strictly convex. If you find the all points where this construction gives us the strictly convex, then R is the interior of a concentric ellipse. Concentric ellipse, concentric cycle, but if you have ellipse, there's concentric ellipse. The scale factor 1 over square root 2. Yeah. So then if this is the radius of this cycle, then the radius of this is radius of that over square root 2. Yeah. And so on, and so on. Next, yeah, it is a global central symmetric transformation. So, so that's what I wanted. I want to in calculation, but calculations that play a bit with some constructions, because you can make everybody who is watching me can try to use Mathematica or Maple or MATLAB or something, and there are beautiful visualizations you can get, and such that nobody saw before. So that let's me show you some done by this. Set this construction is oh yeah, you see, this is the situation. Like That's easy to see. You see this oval. This oval is this curve. This curve. This is just curve of constant width. Whether you take the parallel lines, the distance, because this is easy to calculate. You do this also in your co-laboratory. I think each mathematician, each student, and each scholar and member of the college, this college we are now, they should have a home laboratory. And then you see the point. This is that point. This is that point. And the construction computer does. I mean, takes these lines, and then I change the point. Like go to the center. Calculate. Calculate. You know, she calculate. I can make some doing. You see, and then no, that's because yeah. It's calculating, but we should know. Maybe now it's easy to see. The sizes. So then let's manipulate this point. Now, if you are here, more or less in the center of this oval, then the center transformation is on. Then experimentally we can go this direction. Or it's still convex. But you see how it changed. That was triangle more, but that's not looking triangle, like square or something. The transformation is and over. And coming back to the boundary, so let's come back to the boundary from this. But I cannot continuously move because this this laptop. Because you know, in our world we get used to them as a live friend. Okay, then let's come back. Come closer. Oh, you see, and the light square. But of course, it is construction, which seems, if you show on hands, this seems what calculated to write the formulas is so. Then students can do it. Then you see, I'm closer to the boundary. Is changing, and let's more close. Close and more close. And then you might see, just wait. Oh, somewhere you see here, there is a inflection point. So that means that closing the boundary, we just transformation is non-convex. Non-convex. And if this is kind of flat part like here, you have to be quite close. Okay, what is here? Here. We are going to the less flat part. Oh. So then You see, even here it's already convex. Yeah, then let's find it. So what we try to find, just the points of the boundary of the region where these transformations are convex. So then when they start to be non-convex, this point, we mark that points where this transformation is not just non-convex. Means that there are points like here, you see, like here, on the dotted line, where this is almost flat. There are two inflection points. They scatter. Then you see if you are coming to the boundary, this way is more and more visible. Visible, less visible convexity is just on the boundary. This is the generated. It's now you see the river. Then this guy is convex. Nice. Not convex. Not convex is not very good. And then if you come even closer, then with this. And what happens if you go outside with that point? If you go outside, so for example, here. Wait. Oh, you see? This is something like that. This is kind of 8 number. I mean, this is, let's be closer. It is like that. If you go through lines past that point, you get a kind of self-intersecting object, which is so not only non-convex, but also having singularity. So outside ovals, outside beautiful shapes, there are also singulars. Inside, there is a soul, there is a center of the body, of the previous body, which is also. If you are inside, you should go outside. So if you are convex, you should be in some area to see where you are. You might be there. Otherwise, other places can be there. Or outside, you see another area. Intersection to something very strange stuff. Let me do this also here in that one. You see, yes, maybe even better see. This is the center of the symmetric transform. You have this non-symmetric. You can transform it to be symmetric. You are outside, but it's self-intersection. It's really like that. If you think that for a while, it's really like that. Also the sun. Not so like that. Yeah, very far, maybe here. Very difficult. Oh, why this is so? Because if you go the line to that point here, and this is very small, the interval here. Let's say, if this is tangent to that, then this line passes through this tangent to that. So this is just the point. If you go with this, if you rotate this line, this is beautiful, believe me. I tell it to the students watching us. Maybe they are still there. Maybe they don't like, but like that's also okay. Okay, so you can play with this. If you do this by yourself, but this is not so difficult, but this is done, then you will be very satisfied. Also, I think that was the master, but not only master, but also friend. This is, I know many masters. Okay, let's. And then yesterday talk. I also people I hope on the internet those who were also yesterday. So let's. Yesterday I also had showed some mathematical. See, we have the same oval, but we have interval. I mentioned this yesterday. So let's see. See, let me explain what is this. What is this? That picture is like that. You take the interval, this one, and you go, and the curve is fixed. This curve. This is, you see, this is the curve. This is constant. This is the curve. And then you take interval. And you just do that like that. Maybe you should, maybe I should tell you this on the blackboard because this is easier. You know, if you have, say, this, take the interval, and then you move it, keeping this ends on the slide. So the next one is that one. Is that one? See? But this length and this are the same. So you are going around in this of the same distance, of the same length. So you have, for example, this law, like that. Yeah, but this is too slow. So, but if I have smaller, you see, like that, then you see, I can go like that. With the same length of the interval. That is done here. You see, this interval is the same length here, and so on, so on, so on, so on, so on. This one is not affine invariant because the length is not affine invariant. The length of the interval, because if we have no metric, then length is not there. For construction, you may see that you can mix Euclidean and no problem. So then you see what's going on. This is the density. This is the length. This one, this is the length of this interval. LS is the length of the interval. So if I make it smaller, you see that this is n1 is n1 of this interval. So you see, so that's like that. And if I make it longer, then you can see how it looks. Oh, you see, this is still the same interval, the same length, but n1 number of these intervals is not big. I think that this is bigger. And then if you make this number bigger, then you see something what is only visible in divisional situation of going to infinity. with the number, it is the envelope. Envelope of these intervals, you see, is some path like that. Beautiful path, but if you take the interval a bit longer, or then then you have something singular. What about about this singularity I will tell next course. So you see, so there are something like that. Of course, if you go with the number of lines so much, then right here, then you keep this triangle. In fact, this one will almost this is see that this is some shape here of some two paths and some intersection. And of course, if you consider the longer interval, this is like that. It's beautiful. But of course, this mixture of evident and Affine. We are not okay. And this is just for exercise. For exercise. Of course, if you see if the curve is complicated, this is it's such simple fraction that this is simple to calculate. For this case, this is the curve just constantly or parallel equalizing always the distance. It is very useful shape in okay. Now, but today we will do in 2 minutes, 10 minutes, in 10 minutes, or when we make now. Okay. Yes. Okay, so let's make this good moment for the game. Thank you. Right now. You understand? But then singularity always, you know, not Just a moment. So we start, yeah? Okay. Let me now show you a Maple program which calculates these things. This is not extremely difficult, but needs some knowledge. Of course, for curves, for surfaces, we use some techniques. One technique is, say, for curves is support functions. Support functions. So that's well known in literature, but it's not for each curve. So some curves you need to find as your own method. So then how we do this? Or for example, let's open some program like this one. Yeah, so then we have this the curve, the curve, and then we do this calculation. You see, this is the program making in Maple. Let's as you see, the standard is not so difficult for such curve. You see, you take some point here, and then this calculates as this is even, you see, this is even two such non-convex regions. So then, yeah, and then this calculations are done by this program. That's yeah. In this way, you make experiments. Mathematics is experimental science. I mean, not only say kind of calculation experiment, but also the brain experiments. Then let me check another program. Let's say maybe higher inflection we see, because as you see, this is this. Now, these are a lot of calculations. You see, a lot of calculations, and sometimes there is only calculations. And then this is for the high dimension. So, if dimension is growing up, then the calculations are really much more complicated. It is interesting that our mind is doing this much easier than computer. But it's some yeah, so then maybe, and what's the idea? Let's put to the, so you see what I'm doing here. Let's close this and to destroy something. And come back to the presentation. Singularity presentation here. Presentation is letters. Yeah. Sorry. Okay. Let's quickly go through this presentation. You remember we were with the side, the ellipse side, and then the calculations. You see, the calculations looks like that. You need not to be very, very stressed of the advanced of these calculations. Usually, there is a kind of using the thinking properly, geometric thinking, using the proper functions and so on, and then you can calculate. So the most important problem in these calculations is to find inflection points. Inflection points on the transformation. So inflection points is just the formula for these inflection points. If there is the this is transformation, the central symmetric transformation of the side. at point P. If P is 0, then you have just you have the cosinus t, cosine t. Just a point. And then so that I already, these are examples, you see, of the center symmetry transformation for the constant width. The blue one is the transformation. You see, if this is very close to the boundary, then and the blue one should be here, but that's matter. It's drawn on the central kind of position. So if we are here, then you see this even appears something not smooth, but this is still smooth. Still smooth. The only if this is on the boundary, then this is collapsing. This is tangents, right? This collapsing is tangency means that this is if you go, this is coming back, and if this is exactly, oh, you know, this is not on the boundary. It's not, some small distance. Some very small distance is bigger distance here. Yeah, but this is just the because you understand this. Yes, yes, of course, outside. This thing should be here. But this program calculates it, everything comes to zero. It calculates this. The program calculates this blue and put it here, not here like it should be. It should be here. But the shape is important. So for example, this is the oval. So, and then you see this tangent line, the point is here, is just the line to which both sides are tangent. Yeah. And so, yeah. And then the calculations might be done, for example, of two intersecting straight lines, rounded triangles, and so on. Then, if you write this type of triangle, you can just very easily write a formula for this interval. You PQ point, and then you find something new. And the formula for center symmetry transformation is also given symmetrized like that. Then we get finally the hyperbola. I go through this quickly because these are calculations which you can always figure out by yourself. And also, if you this red one is not smooth, you see, it might be like triangular, not like this smooth one we had before. And then also the calculations are, you see, that guy is just the center symmetry transformation. If this is inside, you see, then we have something very interesting because this is 1, 2, 3, 1, 6 intervals. This is just the angles. It's not sharp. But this is not also sharp. The angle is finite. And you see that sometimes it's not always convex. And here, if we make it smoother, we can smooth up these corners. Like engineers, they do not know how to do this. They take something and make it not sharp. And then you have this blue one. It's also not sharp. You see, second one you have some shape like that, but this is smooth. And if this is more sharp, then this non-convexity start to appear. So for such, how to say, not smooth case, there is no soul of convexity. So this is convex, of course. This triangle is convex, but that's enough. I mean, even any point here belongs to its soul of convexity. This is convexity, which is just very poor convexity, extremely poor convexity, because these are lines. So then we calculated also many of these. It's interesting to find the area where this transformation is convex. Okay. Then then now what I was talking about, the point is approaching the curve. The point is approaching the curve. Now this is written in the proper place, not in the center. Then you see this non-convexity start to be closer and closer, and finally the point is on the curve. Then you have, this is even for the cycle, you see, even for the cycle. Then you have two cycles, you have tangent side. So this tangent is just tangent for that. And then if you go out, then you can see this, that this line is tangent to the red. It's tangent also to the red. This is zero. It's the same this direction. But if you take this direction, then you have this interval, which is left of you move, then you have this point, this point. So you do the pictures, but you know that outside is something like that. And of course, this is cycle. If you have more complicated figure, this is much more complicated. But what does it mean? Our mind likes complications because recognizing some structure usually. Because I don't know if now artificial intelligence can do what our brain is doing, but our brain is going to associate many things at the same moment and create something new. But maybe very soon. And then propositions is formulated. This is formulated in the proposition. What we get if P moves across the boundary, across the square. So if it moves across C without an reflection, CST changes from two smooth branches with two inflections, each changes P inside C through the two smooth branches with ordinary tendency, P on C, crossing with each branch having an inflection. But this inflection is in that point. This inflection is that point. For a smooth closed strictly convex curve C and the base point is closed, inside C, the CST is never convex. So that means the boundary of the curve is always very risky. Never you transform to the convex. And then we are just, this what we are doing this. I'm doing it because we're doing this because we want to understand how does look like the set where the boundary, this boundary of the set is very simple, cycle. But find this in other tests. And what kind of singularities this set can have? It's a completely new invariant. Affine. This is everything the case in affine invariant. Why? Because construction is affine invariant because they are the center of the interval. So then if you look from other side, if you transform by matrix, there is still the same property. So in mathematics, sometimes people forget that when they are studying in mathematics, they study invariant. But not necessarily integrals and invariants and so on. And so on. Of course, we study how to calculate some integrals, but in fact, a lot of things are because they are invariant. Some people balance. So, so that's how does explain this phenomena outside of the curve and passing through the curve. That's sections to a standard Whitney umbrella. Whitney umbrella is the set. You know, Whitney umbrella is the set. You might have it. It looks like that. This is just the Whitney umbrella. And so this is the set. And you can write easily this x squared y minus equals 0. If z is, you see, if z is equal 0, if z is, just a moment, if z is equal 0, then y equals 0 is the line of x. So if this is y, this is x, then if you put z equals 0, then you get this line. So this is y equals 0, that's defined. Then if you take z positive, then you get two lines. See? So if you are here somewhere, you get two lines. Two lines, just two lines, because x squared minus y squared meaning two lines. But only moving the angle because of z. And this is just the equation of this. It's very important because it is stable. I mean, as a image of the mapping of R2 into R3, stable mapping. So not many stable mappings of R2. Next course, I will tell about that. So you will see the beautiful shapes which are persist, which are not immovable, which are not accidental. It's impossible to move them by small perturbations. And the author says that just this phenomena is the intersection of this Whitney umbrella by plane, passing through slowly by this plane. Yeah, so then this is just explanation why this is. And then how to calculate these calculations, you know, always you need to choose some method. This is for high reflections and the you take two pieces of the two pieces of this curve, parameterized, and the lower curve and upper curve are written that. You also use the maple or something to calculate. These are usually Taylor extensions. Not necessary to have everything. I mean, it's enough a few on the terms of the extension to calculate properly. And then for linearity origin to origin is type. Yeah. And then we solve the situation to do substitute to f. Then he gets the just some equation which gives us the so the condition. This is the parameterization of the curve. And then the condition for cutting reflection on the center sliver. That's derivative of size variable. This is easy, but inflection point, it's not. Some people think that inflection point is done when this is something like that, then of course this is inflection point. Yeah, if you y x cubed. But if you have just like that, then there is no let's say this is coordinates. Then it seems that everywhere the derivative is positive. Yeah, but the inflection point is here. See, this is changing the derivative sign of derivative, convexity of derivative, the second derivative is 0. So then this is the inflection point. This is inflection point because the tangent line is going down and decreasing, and then of course on the curves we have such. Why this is, for example, usually we draw the picture of non-convex body. Yeah? This non-convex body. Why? Two inflection points here. Two inflection points. This one, that one. There are two inflection points. And if this is, like, by these scales, coming inside, then we have something which gives you almost flat. So then this is high inflection point. If these points are going together, then we get this one, which is high inflection point. So inflection points, inflections are more advanced singularities in the singularity. So much. For singularity, people use everything. So the conditions for high inflections are written here. You see, these are these conditions. So there are. This is the first condition, first inflection, and this is a second inflection. This is these two with this type of higher order inflection. So invisible, almost flat, but this is really, if you think about it, why you will see that it's a very beautiful geometry. Geometry, maybe even not geometry because it's not much space you use. But you take from geometry something to your brain and create the brain geometry. Geometry that means that you measure the air. So you leave air and do that. Okay, and the calculations, these calculations are messy in some sense. This is a double inflection point that the base point is a point for which the endpoint occur at certain rate inflections in the system. We afforded to. So this is just this type of things. And now what is so important for us is just the local structure of the set, which is the boundary of the set of the convexity. The convexity of central symmetry sets PFP. Let's suppose that the conditions 1 and 2 hold, so that the pole going 0, the 0 is double inflection, both for CST latitude 0. Then the pole is tending to the local CCST boundary. Local CST in the moment I show you. And then what is also, so then if you remember, if we have this kind of curve, and then what we try to find, that's the boundary of the set. On that point, this is boundary of the set of the central symmetric set is the non-convex. So based on convex convexity, there is convex. It's a boundary kind of between non-convex and convex. This is our aim, to find this set. big class of the curves. Also the two-dimensional case. And these are called conditions in the. So this is a published to show the paper of some of the rest of the those text. And then this is the some how to construct the tangent lines to the because if we have the set smooth. If we have tangent lines for it, if we have tangent boundary, then we have the set. So then this is the construction, how to construct the tangent parallel or tangent to this calculation is very, I mean, this is the algorithm, how to calculate. So the best lines are tangents to the given curve at the points A, B, take this sides of the chord, and PQ. So PQ is a sort of point, the base point, which you calculate the total set. The lines are down through a parallel to the tangent and vice versa. So you take this points parallel. Take this. This is CB is parallel to A. So this one is parallel to this. You take one. Then this one is parallel to that one. Take those, and then you found this point C. Found the point C, and the point C. Found the point C. This is just all because you got this line past Q, which is the parallel system. The boundary of this. It's just a construction. And this is just how does look like this. These are examples of calculation. Very strange to see. So that is very strange because inside here, your central symmetry transformation is convex. There is non-convex, but it's very strange. Never appeared that we have an affine invariant for curves. So we think so curves are so simple and so on, but they have so much structure. You know, they have so much structure. They have so much structure because they are. Okay, so now very quickly, because I have not much time. Oh, these are some calculations. There's other cases. Also, the 2 dimensions. And this is the papers. Or the small paper, but I only put this two. Then, very quickly, I want to quickly show the kind of presentation about symmetry. Symmetry. The symmetry is so kind I think that we can look without giving away so the art is full of symmetry, whatever you say. But of course, you say a bit disturbed symmetry, broken symmetry, or something like that. And convexity, you see everywhere is convexity, is beautiful. Convex is beautiful. Shape convex is beautiful. Not convex should be in harmony with convex. So you see regularity, structure that you recognize from the ornaments and so on. This is also full of point symmetric groups representing crystals, symmetry of crystals, and so on. That's also. And then packing structures. You know, if you see on the floor, sometimes even this floor, to some extent, is is the packing, but maybe not very regular. But it's enough regular. Maybe some. So you see, this is just the yes, even oh yes, nature symmetry. Yeah, points. This is by visible sides. It's symmetric. It's flowers and so on. Once it is also this is in very strange symmetry, very infinite, you know, covering the tiling of here's the plane by two types of figures. You see, not by one, two types. The Penrose tile. Post-its are very on post-its will be next week. Evolution of post-its and waveform, very beautiful evolutions. Then full of this type of questions. And then and that one you remember, very symmetric also. You remember yesterday lecture. Sample said. And then you remember the waveform, light which is coming. It's light sent by ellipse. Light sent by ellipse. Fractals also, you know fractals. It's iteration of some mapping. Pictures are beautiful. How much they are useful. And also the person's identity. Some psychologists use this kind of views on the personality. So central, usually we have central perception of the world. We are in the center of the world. Usually people are sure of that, but others don't tell about it. But they are centers of the universe. And then, of course, horizon of thoughts and memory and intuition. This is rather this red one. See, this is the red one. This is horizon of thoughts. This horizon. And then horizon of imagination is a blue one. Imagination is always centralized. Imagination has no so big relation to the reality. But it's centralized. So the blue one is just the imagination, which is central. That's exactly central symmetry. So our imagination here, but it's model for the life. This is centralized. So ego, it is our what we are inside. That's isomorphic between just HM and HW. So between horizon of thoughts and between horizon. And then of course we have areas of ego and so on. This they use the names unstable soul. You see, unstable soul. Side of the boundary has too many castles. So this is very bad personality. Not bad, but very strange personality. This personality is nicest. Perfectness of the shapes. So this is this personality because this is just the smooth object. So the soul is inside. And then area of self-relation is also the area of self-relation is just inside. And then objects without ego, completely no ego. So this is artificial, giving something like that. Even a small leaf, I mean, tree has a leaf. We don't recognize it, but it is alive. We should appreciate the life. We should appreciate life. We are not. Oh, right. It is true. Right. Yeah. then the reference is A, and this is perhaps for what say. Thank you very much. For the last moment, I would like to suggest you that tomorrow will be even nicer because we will tell about some. I have some toy, like a magnetic toy, and it is by this toy I show that the model for all the chains which have been constructed for our bodies and so on, and then that you should well, and so I suggest you that tomorrow will be even easier lecture. I mean, easy, but not easy. Thank you.